Hello students, welcome to another interesting session of refraction through a lens. In our previous session, we learnt about lens, types of lens and terms related to lens. In today's session, we are going to understand the image formation by lens. And let's get started now. So, what we learnt in our previous session? So, we learnt about lens. Lens is a transparent material which is part of a spherical surface. So lens is a spherical surface which allows light to pass through it. And when light passes from one optical medium to another optical medium, it undergoes refraction. So refraction means when light passes from one medium to another medium, it changes its direction. So that phenomenon of light is known as refraction of light, and lens is a application of refraction of light. So in lens, light passes and gets refracted and give us different image formations. That is why we get different applications of lens. Then we learnt about two different types of lenses. One is convex lens and another one is concave lens. So convex lens is also known as converging lens, and it converges the light rays falling on it. That is why it is called as converging lens, which is thin at the edges and thick at its center. Concave lens is a diverging lens. This lens diverges the light rays falling on it. So concave lens is thick at the edges and thin at the middle part or at the center. So such type of lenses are known as convex and concave lens. There are so many different types of convex and concave lenses that also we learned in our previous class, like biconcave lens, biconvex lens, plano-convex lens and plano-concave lens, concave convex lens and convex concave lens. And we learnt the structure of the different types of lenses in that. Then we learnt some technical terms which are related to lens, like what are optical centers, what are radius of curvature, center of curvature, focal points like primary focus point or principal focus point, principal axis, secondary focal point, and some other important terms or important things related to lens we have learnt in our previous session. We learnt the differences between the convex and concave lens in the previous session. So let's start with today's session and let's try to understand more about the lens and its image formations. So in this part, principal rays or construction rays for ray diagrams we are going to learn. So in general, we use the following three rays for the construction of ray diagrams. Ray diagrams are the diagrams which will represent us the rays which are falling on the lens and how they are getting refracted and what are the places they are going to get either converged or diverged, or how the images are going to get created using these three principal rays in a ray diagrams to understand the different phenomenon of lenses, right? So let's try to understand them one by one. First, a ray of light will incident at the optical center O. So we already know what is an optical center. The optical center is the center of the lens from where if a ray passes, it will pass undeviated or it passes parallel to the incident ray. So the emergent ray is either parallel to the incident ray or it passes undeviated through the lens. So this will help us to understand the image formation easily, because it is always the same thing happening through optical center if a ray passes. So this is the first principal ray construction. Secondly, a ray of light incident parallel to the principal axis of the lens. We already learnt in our previous session what is principal axis. It is the axis which connects the center of curvature of both the spherical surfaces of the lens. So, what is happening here? When a ray of light is parallel to the principal axis, if it is parallelly coming to the principal axis, it falls on the lens, and when it is going through the refraction and emerging out of the lens, that emergent ray will always pass through the principal focus 2. Secondary focus 2. So, it appears to pass through F2 or principal focus 2. Because it is lying on a principal axis, we call this as principal focus, and it is at the other side of the lens, so it is secondary principal focus. So a ray of light incident on a convex lens, if first case if we take, that is convex lens, then it will pass through the secondary focus. In concave lens case, what is happening? If a parallel ray to the principal axis is falling on the lens, then that lens will diverge that light ray, and if I extend that light ray, then it appears to come from the secondary principal focus point. So this is the secondary principal focus point, and we feel like the divergent ray is getting originated from that point. If we extend that, this is the imaginary ray extension, and that extended ray will feels us like it is originating from, or it is appears to come from F2 in case of concave lens. So this is the second principal ray for construction of a ray diagram, where we can find out where our image is getting formed. So let's try to understand the third one. In third case, what is happening? If a ray is passing through primary principal focus. So in case of convex lens, if the ray is passing through the primary principal focus 1, then after incidenting on the lens and getting refracted, the emergent ray of the lens will pass parallel to the principal axis, will emerge out to be parallel to the principal axis. In case of concave lens also, if I extend the incident ray, and if that ray is appears to emerge out from the principal focus 1 of that lens, then after falling on the lens and getting refracted, and the emergent ray coming out from the lens will be parallel to the principal axis of that lens. So what is happening here? A ray of light passing through the first focus point F1 in a convex lens, or directed towards the first focus of F1 in a concave lens, will emerges parallel to the principal axis after refraction. So these are the basic or principal rays for construction of any ray diagrams. With this information about convex lens and concave lens, let's try to understand the different image formation in different positions placed near the convex lens. So what is happening here? If we take the three rays, that is the ray which is coming parallel to the principal axis, which is emerging out from the optical center and which is passing through the principal focus 1 will all meet at some point in the after the emergence, and it creates a image here, right? So can you see here, the first ray is coming out and that is parallel to principal axis. So what is happening after refraction? It is passing through this principal focus 2 or secondary principal focus. Then we'll consider the second ray which is passing through the principal focus 1, and then after the emergence it goes parallel to the principal axis at the other side. And when a light ray will take the third light ray which is passing through the optical center, which is passing through the optical center. Can you see here? It is passing through the optical center of a lens, then it will emerge out without any deviation. So we have three rays here. One is here, the second one is here, and third one is here. All these three rays are meeting at certain point, and that point is creating the image of our object. Right? So that point is creating the image of the source or the object what we kept in front of the lens. So using these three rays, at the point they meet, that will be our point at image is getting formed. So with this information, let's try to understand the different image formations in convex lens. Now, in case of concave lens, what is happening here? In case of concave lens, again we are considering the principal rays, and the first principal ray is coming parallel, right? It is parallelly passing through, coming out from the object, and it is going parallel to the principal axis. So when it's get diverged, if I extend that, it will pass through the principal focus 2 of the lens. Now we'll consider the second principal ray, which is the ray which is passing through the the principal focus, which is falling on the lens, and after if I extend that, that will pass through the principal focus 1 of the lens, and after emergence, after it get emerged, it will go parallel to the principal axis of the other side of the lens. And if the third case, if I take a ray which is passing through the optical center of the lens, then that ray will go undeviated. In case of concave, it is diverging. It is a diverging lens. So it will get diverged. And when I extend those rays, divergent rays, those rays will meet at certain point, and that is the point where our image is getting formed. So that is the image forming point. So that will be the image of the object in case of concave lens. So let's understand now at different position how the images are getting formed. First case, an image may be defined as that point where the light rays coming from an object meet or appear to meet after refraction. As we saw in the previous scenarios in case of convex and concave lenses, that the three principal rays are meeting at certain point, or they are appearing, if after extension they are appearing to meet at certain point. Then those images formed are categorized in two different kinds. The first one is real image and the second one is virtual image. So in case of convex lens, the all three emergent rays are meeting actually at some point, and that point is creating the image, right? So that image we can take on a screen. We can bring those images on a screen. So those images are known as real images. In case of concave lens, what is happening? After the emergence, we are extending those rays, right? We are extending those rays, and those rays, the imaginary rays are extended, are creating the images. The formed images cannot be placed on a screen. So such images are known as virtual images, right? So the difference between a real and virtual image, let's try to understand that. A real image is formed due to actual intersection of the rays. They are getting refracted by the lens because they are emerging out from the lens, and then they are meeting at certain point. So at that point, the image is getting formed. So these images are known as real images because they are actually intersecting. The actual rays are getting intersected and they are creating the images. In case of virtual image, it is formed when the rays refracted by the lens appear to meet, right? They appear to meet. They are not actually meeting at certain point or intersecting at certain point. When we are extending them back, at that point they are appearing to meet. So they are producing backward images which are virtual in nature. A real image can be obtained on a screen. We can take the image on a screen if it is a real image. If our refracted rays are meeting at certain point actually, then we can take that images on screen and we call them as real images. But virtual images are getting formed by the virtual meet, or they are appearing to meet. The light rays are appearing to meet and creating images. So we cannot obtain those images on a screen. So we cannot obtain virtual image on a screen, right? So a real image is inverted. So real image, whenever it gets formed, it will be inverted with respect to the object. What do you mean by inverted? It is upside down, right? So the if the object is at one position, then the real image formed will be upside down of the object. So that is why it is called as inverted image. So real images are inverted in nature. The virtual image is erect with respect to object. It is of the same position of the object, right? So virtual image is erect and real image will be inverted. The example for real image is the image of a distant object formed by a convex lens. The convex lens, if we keep the object at some distances, we get the real images out of these convex lenses. And concave lenses are creating the virtual images when the object is kept in front of it. So real images are formed by convex lenses and virtual images are formed by concave lens. Right? Now, the characteristics and location of image for a convex lens. So what is happening here? The object position is getting changed. We are changing the object position. So we are getting different nature and different types of images, sized images, right? So we are getting real images, we are getting virtual images out of convex lens based on its position. So let's try to understand them one by one and try to understand how the nature and position of the image is. So let's try to understand the characteristic and the location of image where we get if we keep the object at different positions in front of a convex lens. So case 1, where we are keeping the object at infinity. So if we keep object at infinity, the object will send the parallel rays of light. So the light rays coming from infinity will be parallel to the principal axis of the convex lens. So when a parallel ray of light falls on a convex lens, it will pass through the principal focus 2 of the convex lens. So it was passing through the principal focus 2. So all the parallel rays which are falling on the convex lens are passing through the principal focus 2 of the convex lens, and the ray which is passing through the optical center will pass undeviated. So all the light rays which are falling on the convex lens after refraction emerges out and intersects at the point F2, that is principal focus 2 of the convex lens. So it will create the image at that intersecting point. So the position of the object is at infinity. So we are getting the image at the principal focus 2 of the convex lens. What type of image we are getting? The nature of the image is real. We can take this image on a screen. So we understood what are real images now. So we can take this image on a screen. We can get a real image out of this position of the object in front of convex lens. We also learnt that the real images are inverted. So we are getting a inverted image of that object in a point. So the size of the image is highly diminished. It is of point size. So it is meeting at one certain point, that is the principal focus 2 of the lens. So the image is highly diminished and it is of the size of a point, you can see. So this is the nature and the location of the image in case of convex lens when the object is kept at infinity. Now try to understand the application of this position. If we keep object at this position, what is the application of getting the image? So when we take the magnifying glass or any convex lens, and if we take the source as sun, so sun is very far from the lens, so we can say it is at infinity. So when the light rays come out from the sun and falls on a convex lens, they are parallelly falling on the convex lens. So the convex lens will converge all those parallel rays of light at one such single point, that is the focal point of or principal focus 2 of that convex lens. If we place a paper at that point, that image of the sun is formed as a small point sized image at that focal point, and the formed image is inverted. So it will converge all the parallel rays of sun and place it at one single point, and that point will, if we keep it for a same position for some time, it will start burning. Hope you all did this experiment and you are aware how the concentrated rays will be, right? So this is the one of the application of the object kept at infinity in front of convex lens. Secondly, if we are using a camera or our eye lens, what happens if we are looking a far object? That object will we will get the real and inverted image of that object after passing through the convex lens, right? So these are the applications of the object keeping at infinity in front of a convex lens. Now let's try to understand and keep the object at some other position to understand the image formation by convex lens at that point. So now we are keeping the object beyond 2f1, that is beyond the twice of the focal length of the lens. So what is happening now? We are keeping the object beyond the twice of the focal length of the lens, and the object is creating the image. First we will take the three rays. In this case we are taking two rays where one is coming parallel from the object which will pass through the principal focus 2 of the lens, and the other ray which is passing through the optical center of the lens will go undeviated. These two rays of light will meet at the point and create the image. So the formed image is at the point between f2, or that is the principal focus 2 and twice of the length of focal length of that lens, right? So here position of the object is beyond 2f1. So we are keeping after the twice of the length of focal length of that lens, the object is kept there. So the formed image is between f2 and 2f2, between the focal point and twice the length of that focal length of that lens. So the image will be between f2 and 2f2. Now what nature of the image we are getting here? We are getting a real image because the rays are intersecting there. So they are creating a real image. We already know the real image is inverted. So we are getting a real and inverted image of the object. What is the size of the image? In previous case, we got a highly diminished point-sized image. In this case, we are getting a diminished image. That means it is smaller than the size of the object, right? So the formed image is small in the size than the object size. Now, let's try to understand the application of keeping the object beyond 2f1. So if we keep an object beyond 2f1, and if we are using a camera, in camera we use convex lenses, so we get the clear picture of the subject or object in the camera. So we can adjust the lens beyond so that we get the object beyond 2f1 and we get the real inverted image of that which is diminished in size. So if we are accommodating a large object, we have to use lens at that object at the point beyond the twice the length focal length of that lens. We get the real diminished inverted image, right? Now, a convex lens is used in this manner as a camera lens when the object is not very far to be photographed, right? So, we'll use this for the objects which are not very far from the camera, so that we get a real clear picture of that object. Yeah. Now, in case 3, now we will keep the object at the 2f1, that is twice the focal length of the lens. We'll keep the object at that place. Then what happens? When we keep the object at this place, the object, a parallel ray of light coming out from the object will pass through the principal focus 2 of the lens, and another ray which will be passing through the optical center of the lens. Both will intersect at the point and it creates an image at exactly the 2f2 distance from the lens, that is twice the secondary focal length of that lens. We get the image at the twice the secondary focal length of the lens. So what is the position of object? Position of object is twice the focal length, primary focal length of the lens. So we get image at the twice the secondary focal length of the same lens. So the formed image is real and real images are inverted. So we get a real and inverted image here. Now what is the size of the image? the size of the image is same as that of object. So if we want any object to image to be of the same size, we should keep the object at twice the focal length of that convex lens. Let's try to understand the application of it. So we get a first image here. There three lenses are used to see a magnified image of the tree here, right? We are keeping the lens to get a magnified image of the tree here. So in this case, we are keeping the lens at 2f1 distances from the object and we get the same sized image, right? We get use three lenses here. Now, when the object is between 2f1 and f1, that is twice the focal length of primary focal length of the lens and at between the focal point of the lens, then what happens? We'll take again two rays. One is parallel to the principal axis which passes through the principal focal point 2 of the lens and another ray which is passing through the optical center, and those two will intersect at one point and create the image, and the formed image is beyond 2f2, that is beyond the twice of secondary focal length of that lens, and the formed image is larger in size. So we are keeping the object between f1 and 2f1. So we are getting the image beyond 2f2. So we are getting the image beyond 2f2. So here again the rays are actually intersecting. So we are getting a real image. So real images are inverted. So we get a real and inverted image of the object. In this case, the size of the image is magnified. So now we are getting a magnified image of the object. That means the formed image is larger in size than the real size of the object. So that is why we call this as magnified image. Now let's try to understand when we use projectors. What we do? We use the projectors and we keep the object between f1 and 2f1. So it creates a magnified real inverted image. Now you may ask a question, when we keep the thing in a projector, we are getting normal, not a inverted, but the uh, erect image only. So we are using two lenses there and the both the positions are same, so we are getting magnified and real image, but the first lens is creating a inverted image and then we use another lens to again make it invert again, so whatever image we are getting on screen will be erect to observe. So we are creating the and magnified image using the projectors by the help of lens, and that lens the object we are keeping here at position f1 and 2f1. We can also use the object in inverted position, so we can get the image in the inverted position which is the erect for our eyes, right? So this is the application of the keeping the object between f1 and 2f1, right? So we get a magnified image using convex lens. When we keep the object at f1 at the focal point of the lens, so what we get? The ray which is coming out parallel to the principal axis will pass through the principal focus 2, and the other ray which is coming out from the optical center is also passing undeviated, and the rays are almost parallel, so when they are have to meet or intersect, the point is at infinity. We are getting image at infinity. So position of the object is at the focal point of the convex lens. So the image formed is at infinity. Here again we are getting real and inverted image, but the image is getting formed at infinity, so we are getting highly magnified image when we keep the object at f1 position, that is at the focal point. So what is the application of keeping object at this position? In case in when we are using spectrometers to understand different phenomenon of different atoms and molecules, that time in a collimeter of that spectrometer we are using lenses to get the highly magnified images, because we are studying a very small objects which we cannot see through our bare eyes. So we use the position of convex lens, how the way the object should come at the focal point of the lens, so we get the highly magnified image and we can understand and study the material or atom or molecule which is under study. So this is the application of keeping an object at f1, right? Now when the object is between the lens and the f1, or between the optical center of the lens and the focal point of the lens. So what is happening? The parallel ray of light coming out from the object. In this case, object is here between f1 and optical center. So the parallel ray of light is passing through f2, and the ray which is passing through optical center is passing undeviated. But they are going up away from each other. So we cannot get image as a real image by the actual intersection of these two rays. So what we'll do, we will extend them back and try to get the image here. So we are taking a extension of that rays which are passing through them, and they are intersecting at some point and creating the image over there. So here what is the nature of the formed image? It is virtual image, because not the real rays, or actually the rays are not getting intersected here. So we are getting the virtual image. So what we are doing here, we are keeping the object between f1 and optical center of the lens. So the position of image is behind the object. So where the image is getting formed, it is getting formed behind the object, right? And the same side where the object we are keeping. Now what is the nature of the image? We are getting virtual, and if virtual images are erect, so we are getting virtual and erect images. What is the size of the image? The image size is magnified. It is not highly magnified, it is a magnified image. So let's try to understand the application of this. We are using magnifying glasses. So these glasses, when we keep in front of a book, or if we are reading some very small script, or the uh, the goldsmiths or the watchmakers, are if they are using these magnifying lenses, they'll get a magnified image of the object what they are trying to look through the magnifying lens. We also use the magnifying convex lens in case of microscopes, where we are trying to enlarge the image size, right? So these are the different 6 cases where we kept object at different distances in a convex lens, and we got the different images and applications of keeping the object at different positions in case of convex lens. Now let's try to understand the concave lens. So in case of concave lens, again we'll consider the 3 principal rays and we'll try to get the image formation by concave lens. So here let's try to understand this. When the object is at infinity, the first case what we took in convex, There also we took the object at a infinity. Here we are getting the object at infinity. So what happens if I keep a object at infinity? The parallel rays of light are falling on the lens. We saw in case of sun, when sun is sending a rays of light, the rays of light falling on lens are parallel to principal axis of that lens. So the rays of light are falling parallel to the principal axis. So they are getting diverged. So we are extending them that divergent light rays, and they are intersecting at focal point. When the parallel ray of light falls on a concave lens, they will get diverged, and if I extend that extended ray will pass through the principal focus point, primary principal focus point of the lens. So the rays are passing through the primary principal focus of the concave lens. So the image is getting formed at that point. So what is the position of the object? The position of the object is at infinity. Where the image is getting formed? Image is getting formed at the principal focal point on the side of the object. Now what is the nature of the image? We are taking the extended rays to intersect and form the image. So the image formed is virtual. The virtual images are erect. So we are getting a virtual and erect image. What is the size of the image? If we keep object at infinity, we get highly diminished or point sized image in case of concave lens. Now what is the application of this? We use concave lenses for the eyesight corrections. We use the convex lens, and then that converging, it will converge at some point. No, before that we'll keep that concave lens. So we get a point sized image in front of our eyes. So this is the application of object keeping at infinity, right? Light from object like moon is falling on a convex lens, and then it is falling on a concave lens, and it is forming a point sized image. So we can use this in a telescope. So this is the construction mode of telescopes, where we get the bigger sized image in images in a point sizes, right? So this is the application of object keeping at infinity in front of a concave lens. Right? Now, the second case, in case of concave lens, we can keep the object between a finite distance from the lens, that is between infinity and the optical center of a concave lens. So what is the image we are going to get here? When we keep any object in front of a concave lens at any finite distance from the lens, we saw already what happens in case of infinite distance. We get a image, virtual image at the same side of the object, right? We are getting at the same side of the object, and the formed image is smaller in size, right? So at a finite distance from the lens, we are keeping the object. So we are getting the image between the lens and the focal point of the lens. The image is formed between the lens or the optical center of the lens and the focal point of that lens. The formed image is virtual and erect. The virtual images are erect. So it is forming a virtual and erect image. What is the size of the image? The size of the image is diminished. It is becoming smaller in size. We are getting a diminished image of the object here. Now, when the object is at finite distance from the lens, that is concave lens, what is the application? Here we are using that for the correction of our eyesight. So we are getting a eyesight correction using the concave lenses, right? Now, differences between image formed by a convex and concave lens. The image can be real as well as virtual in case of convex lens. If we keep object at different positions, we are getting different nature of images in case of convex lens. So if we keep the object at infinity, at beyond 2f1 and at 2f1, between 2f1 and f1, we are getting real images. In case of the object keeping between f1 and the lens, we are getting virtual image. So we are getting both the type of images using convex lens. It is real if the object lies beyond the focus, while it is virtual if the object lies before the focus. Now in case of concave lens, we get always virtual images in spite of any position of the object, whether it is at infinity or at any finite distance from the concave lens. The object is forming virtual image all the time. So in case of convex lens, the image can be magnified, or it can be of the same size, or it is diminished also. So it is magnified if the object lies before 2f of the size, if the object is at 2f, and beyond that the diminished object size we are image size we are getting, right? So the image is always diminished in case of concave lens. In convex, it will be magnified, same size, and diminished. In case of concave, it is always diminished image. So in convex, it is real as well as virtual. In concave, it is always virtual. In convex, it is magnified, same size, and diminished. But in case of concave, it is always diminished. Now the image can be inverted as well as erect in case of convex. So the image is inverted if the object is beyond the focal point, and it is erect if the object is before the focal point. So we get both the type of images, that is inverted images as well as erect images. But in case of concave lens, we always get virtual image. So we always get erect images. So these are the differences between the images formed by convex lens and concave lens. Now, in today's session, what all we learned in today's session? We learned about principal rays for image construction. We took 3 rays where the first ray is coming parallel to the lens, so it will passes through the focal point of the other side of the lens. And secondly, we are taking the ray which is passing through the optical center, which will pass undeviated and non-refracted. Then third case, it is passing through the primary focal point. So it is after emergence, it is passing parallel to the principal axis. Using these three principal rays, we are constructing our images. So we learnt about what are real images and what are virtual images. We also learnt about images formed by convex lens at different positions. We also learnt about how the images are getting formed by concave lens and their applications. We learnt about the difference between image formed by a convex and concave lens. So, what are the differences between the images of convex lens and images of concave lens we learnt in this session. With this, we'll conclude this session, and in next session, we are going to learn about lens formula and magnification. So, thank you for listening this. Thank you.